All right, so the first buffer overflow there was just leaking data from one variable into another variable. But now let's move on to this one, which is showing you the real story of the kind of Aleph-Null buffer overflow, which was responsible for all the malware, whole generation of malware, up until Windows Vista, when the defenses against this exact attack came in. But all the attacks since then have all been variations on this one. So this is at the heart of it all. So let me shove my instructions to the side and bring up my Linux machine. All right, so I'll clear this. Yeah, that's right, just in the middle of some command. All right, so this is ED203. All right. All right, so the first thing I'm going to do is get rid of address space layout randomization. This is a defense measure that randomizes the location of things in memory. And it's important, but we want to get rid of it to make this easier to understand. So this is how you turn it off. You hit this system kernel variable called randomize VA space and make it 0. And then I'll exit back to a normal user. And now I'm going to get the vulnerable program. I'm just going to download it from my server and get the executable version of it already compiled here. All right, and wait, no, somehow I got the same thing twice. Its copy did not work. That's rude. That's the right one. There we go. So now let's do ls -l and see what I have. All right, I'll just remove that extra one. ed3a.c.1. There we are. All right, so if we chmod to make it executable, ed3a, then I can run it. All right, and so you have to be run with a string, and that's fine, so it's running. Now let's take a look at the source code. All right, so this one here has a main routine here, which takes arguments on the command line. And the only thing it needs is that one extra argument, which is going to be a string. And then it's going to call copier on that string. So whatever you pass in, it passes here as a string variable. And here it passes in a pointer to the string. And it has a buffer of 1,000 characters. And then it does a copy of string into the buffer. So that you've got, hello, good morning. So we've got room for 1,000 characters, and you're copying in data that came from the user. So let me, all right, so if I run this program, I'll make this a little bigger. On a short string like hello, it works with no problem. And I know I have room for 1,000 characters, so it's going to need more than 1,000 to make it crash. So for that, we're going to need a fuzzer. So let's make a fuzzer. And we can make it in Python. This is actually the Python 2 version of it. And I don't really want to use Python 2. I'm not even sure I have Python 2 on my Mac, so I'll make it the Python 3 by just putting parentheses around that. There. And so this will take whatever data is passed in. In fact, let me make that Python 3 explicitly here. That's probably the best move. All right, let's see if this works. Might not work on a Mac. Chmod +x. Fuzzer. Let's see if Fuzzer works. Good. If I give it something like this, and it just needs good. So whatever number you put there, it'll print that many A's. And I can put a big number there, and it'll print 1,000 A's, and that's what I want. So now I can run ed3a. I'll clear. Okay, if I, whoops. All right, so if I run ed3a, I can include the output of the fuzzer this way. And so I can feed in 1,000 characters, and it'll make that string and feed it into ED3A. And as you see, nothing goes wrong. It runs without crashing, printing out the pointer and then saying it's done. But if I give it 2,000, I get the segmentation fault. So this is your indicator of a classic buffer overflow. It has attempted to write to a location of memory that it's not allowed to write to. So to find out what happened, I have to use a debugger, and we're going to use the Canoe Debugger in the quiet mode just to avoid printing an irritating message on ED3A. And now in here, we can run it with that same parameter. All right, and if we do, it crashes, and you see when it crashed, the contents of the instruction pointer was 41, 41, 41, 41, which is AAAA. So some of those A's I inserted ended up in the instruction pointer, and you can see more by doing info registers. This shows you the condition of the registers in the processor when it crashed, and you can see that EIP is 41, 41, 41, 41, which is 4 capital A's. You can also see that EBX changed to 41, 41, and so on. So this gives you some of those 2,000 characters ended up in the instruction pointer, and I'd like to know which ones. So I need to narrow this down a bit. So let's shorten this to like 1,100 and see what happens. Start it again, and again I get the same crash. Now let's try 10, 10. And I don't get a crash, or to be fair, if I do get a segmentation fault, but you see it crashes somewhere else. I don't get this message that the data I put in ended up in the instruction pointer, so 1010 is not as exploitable. 1020, however, is enough to make it crash, and now I know it'll be somewhere in the last 20 A's that went in, because I know 1,000 A's will be handled with no problem. So the last 20 A's were enough to make it crash. And I should be able to gain control of the machine then. So for that, I'll make a different program, and I think I'll just exit, simplest way to do this. All right, quit, I guess. All right. All right, so clear. I want to make another fuzzer, which is going to be Nano EX1. And here it is. And I just want to make a couple of changes for my system and make this Python 3 and put parentheses around the thing that's being printed to be compatible with Python 3. So instead of sending just a lot of capital A's, it sends 1,000 A's and then 4 B's, 4 C's, D's, E's, and F's. So the total length is 1,020. And the point is now I'll be able to see which characters ended up in the instruction pointer. So I save this, make it executable. And if I run it, see how it's working. It does what I expect, 1,000 A's, and then B, C, D, E, F. So if I go back to GDB, I can run, taking output from that, there. And now when it crashed, I get 45, 45, 45, 45, 41 is A, B, C, D, E. So the E's right here are what ended up in the instruction pointer. And I can see the registers with info registers and see that the base pointer contains A, B, C, D's, the BBX contains C's, and the instruction pointer contains E's. So now I know my buffer overflowed and the extra characters ended up in the instruction pointer. I can now control the code. All right. So now I make I can make some exploit code. You can make your own shell code, but we're just going to use standard shell code. Let me see if I have Metasploit on this machine. I need quit again. All right, I need MSF Venom. Let's see if it's there. Yes, I want to quit. MSF. I do have it. All right. And I have instructions in the project how to install Metasploit if you don't have it. It goes nicely on any Windows machine or any machine of any operating system, but we're using Linux. So this will show MS Venom payloads, and then look for Linux and bind TCP, which is a simple attack. It's kind of slow. This thing is written, I think, in Ruby. Okay, so there's a lot of them, and the one I want is Linux x86 shell bind TCP without that slash. This one here. The reason why I want this one is it's the simplest. It's not staged. The staged ones have to load a second bunch of code from the server. This is the simpler one that puts the whole attack in just one exploit file. So to use that one, let me clear. This is going to execute that exploit and just list the options so I can see what other parameters I might need to set to create useful shellcode with this MSF Venom. Okay, and so there's a bunch of parameters, but the basic options are here. The listening port by default is 4444, and that's the only thing you really need. There's a bunch of other options, but none of those are commonly needed. So to generate a simple Python exploit, I can do it this way. I can set the local port to be something else if I want to, the listening port, and that didn't, there we go. So here what I've got is a command that will change the listening port to 31337 and write Python code. So it's ready to insert in my Python exploit file. Okay, so there's the file. It only needs 78 bytes. The Python is 389 bytes. So it will definitely fit in the 1,000 bytes I have to work with. And there is a problem, however. If you look at this, it often contains a null byte. Now this one might not, but it often does contain a null byte when you do this. There it is. It does contain a null byte, which means it's not going to work. Because remember what's going on here. We're taking a program that reads a string from the input. And if you remember from the earlier command injection vulnerability, a space would terminate the string. A null byte will also terminate the string. So if I try to inject this, I'm only going to get the part of it up to the null byte, and the part after that is not going to be accepted by the program. So I can't use this kind of shellcode for this kind of attack. What I have to do is get rid of the null bytes. And there are other characters that would probably be bad too, like space and tab and carriage return. So the simplest way to deal with it is this way. Let me, if I can get my caps lock under control. Okay. You run it again, and then you add alpha mixed. Encode x86 alpha mixed. That will encode everything as printable characters, which is what I want for string. And I also found it's good to use this advanced option, append exit equals true. That makes it run better. So there we are. Now I have a longer exploit, but it's still only 230 bytes. So this is, and you can see these are all now much more printable characters. 30 is the number 0, 41 is a capital A. These are all printable characters. So I want to add that to my Python file. So let me, I'm going to do it like this. I'm going to copy this stuff. All right, and now I'm going to nano ex2. All right, I'm going to paste that stuff in, and I have to add some more stuff around it. So at the top, I'm going to need this, Python 3, and then all the buff lines to define my attack, and now I'll need this stuff. Okay, and so what I'm going to do, remember I found out before that when I took 1,000 and then I added characters B, C, D, E, F, it's 1,012 is the number of characters it is before you reach the instruction pointer. So I'm just putting in dummy values. For my instruction pointer, I'm going to put in 1, 2, 3, 4. And here's my buff. So I'm going to have a capital A's. I'm going to have 1,012 capital A's minus the length of the NOP sled and the length of the buffer. So here's the attack. A NOP sled and a buffer and a suffix, which is a bunch of A's, and then the instruction pointer. So let's look and see what this looks like and understand what it's doing. I'll put parentheses around this so Python 3 will accept it. And now run that. Let me make it executable. And run it. All right, can only concatenate strings. The problem, since I'm trying to do it in Python 3, I need to make this, these need to be byte values in Python 3. There. Let's try that. All right. So now you see I've got NOP, 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 NOP. These 90s are no operation codes. That's a NOP sled. Then all this strange printable characters here is the actual exploit that's going to open a listening shell, convert it into printable characters, then a whole bunch of A's to fill in the storage variable and get to the instruction pointer, and then 1, 2, 3, 4 where the instruction pointer is. All right, the other thing I noticed is it printed as a byte value, and I need it to print as a string to feed it into my exploit. So I'm going to make the attack into string of this. I think it's str. See if that works. And it does work. Oh, nope, still bytes. All right. Maybe it's that thing to string. Hold on a minute, I'm going to check that. If I go here, Python 3, bytes to string, convert bytes to a string, yep. String of text bytes work, can't specify the encoding, that's what I thought. I have to do decode. Right. Let's try that. So it would be I think decode.decode. See how this works? I might have to decode it as Latin 1 or ASCII. All right. Got to get rid of the string I added. All right. Decode. UTF-8 is an option. Text bytes, decode, UTF-8. I think what I really need is Latin 1. Let me try it. That's what I get for trying to switch from a different version of Python so quickly, but this is an old project. I think it's Latin 1. There we go. Now I get printable strings, and notice the 90s are not printable, the NOPs, so they show up as blank space. Then you get the Metasploit shellcode, the padding, and then the instruction pointer. So now you can examine this in the debugger. So if I do gdb minus q of ed3a and I run it with this, if I run on $ex2, it gives me a segmentation fault. It ends up with funny characters here, but we're going to put a breakpoint in so we can watch the buffer overflow happen. So let's disassemble the copier. All right, this is the code that has the buffer overflow, you can see here's where it does the string copy. This is where it copies the long string into the variable that isn't big enough, and then it's going to return after that. So I want to break here. So it'll stop executing right after doing that copy. In fact, I want to break before the copy and after the copy so I can show you the difference. So I'm going to copy this and put a breakpoint there. I'm going to put another breakpoint at 41, which is after the copy. And now let's run it with that input again. Start from the beginning. All right, and here we are. We've hit the string copy command here, and if we look at info registers, you'll see the instruction pointer is still pointing to the next line of copier, which is normal. And now we can talk about the stack. ESP and EBP are the top and bottom of the current stack frame. And you see it goes from CAF0 to CEF8, which is ABCDE 400 in hex, which is 1024, which is what you need to store this 1000-character string. And we can examine that with X, examine 400 bytes of hexadecimal starting at ESP. You just need to remember that EBP is CEF8. So that's only taking us to CC, and CEF8 is here. So this mess I'm about to highlight, this is the stack frame. From there all the way down. That's where the stack is stored, and at the end of the stack frame is the return pointer, which is where it's going to go when it's done executing. And you see that's this 804. 804 are the addresses that you see in the main code. So this is the way it works. Now that's before the buffer overflow. Now if I continue the program, it'll go to the next command and have the buffer overflow. Looks like if I continue, there, it moves to breakpoint 2. And now, if I examine that stack frame again, see now, it is starting with 90, 90, 90. And I'm seeing some funny C2s in it, which trouble me. But anyway, let's try the next bit. Yep, then come my 41s. And the end of the stack frame was at F8. Here's the 1, 2, 3, 4 I expected to hit. Okay, let's look at my registers. Okay, the stack frame ends at from AF0 to EF8, CEF8. All right, and so that is up here, and you can see that's where the 49, 49, 49 hit it. And so there's a problem with my exploit. I need to fix it. These should all be 90s, and there's got a C2 in it, so something's going wrong with my Python code. So let's quit from here and debug the Python code. All right. That is EX2. All right. And let's run it. I see. It's got to do with that translation. Let's see if I have Python 2. That's the easiest answer. And I do. All right. I'm just going to go back to Python 2 because I'm having trouble converting that code to run in Python 3. So I'll get rid of these B's and we'll just print attack. And change that to Python 2, and maybe it'll run right then. It's my decoding of bytes back to strings that is somehow preserving something bad like those backslashes. All right, that's what I wanted. You have the unprintable NOPs, and then the buffer. Okay, this looks pretty good. Let's go back in the debugger and disassemble, copier. Here's where the buffer overflow happens. So I want to break at this point. So I want to examine the condition of the stack after the buffer overflow. And so now I run, taking the input from ex2. It hits the breakpoint, and so now if I do info registers, my stack goes from CCF0 to D0F8. So if I examine it with X400X ESP, remembering that the base is D0F8, there we are. Now I just have 90s. And here's the Metasploit shellcode, and here's the padding of capital A's. And this looks right. D0F8, this is where the stack frame ends, and this is the next byte, which has my pointer, which is just 1, 2, 3, 4 in ASCII. 31 is a 1, 32 is a 2, and so on. So now, if I just continue, it does put that value in the instruction pointer, 1, 2, 3, 4. So my exploit doesn't work yet, but that's because I put in a dummy value here. This is going to go in the instruction pointer. To make the exploit work, I just need to change that address to an address in my NOP sled up here. And anywhere in the NOP sled will do. So I'll just pick an address in the middle. That one will do. That's what I want to put in my exploit. So let's get out of here and copy EX2 to EX3 and edit EX3. And the only thing I have to do is fix this instruction pointer here. So I'm going to save what's in my clipboard as a comment. There. That's the address I want. Now, unfortunately, since Intel is little endian, it stores these addresses backwards. The bytes are backwards. So you have to put in \x E0 CD FF FF. That is this address with the bytes reversed. So if I've done that right, this will now jump into the exploit and run it. So I try it in the debugger again, and I'm going to disassemble copier again and put in a breakpoint so I can test things. Right here is the point right after the buffer overflow has happened. So I put a break there. And now I run it, taking input from EX3. All right, now I take a look at info registers. It stopped right after string copy. Again, the stack goes from CF0 to D0F8. So if I examine that, D0F8, okay. Wait, that didn't work. I hit the wrong button somehow. Let's quit that. 400X. I wanted to see it in hexadecimal. There we go. So there's the NOP sled, there's the exploit and the padding. And D0F8 is here. Good. Okay, so that's the end of it. Here's the pointer, FFCDE0. And CDE0 is up here. So it looks good. It looks like if I continue, it's going to make it into my exploit code. And it does. And it doesn't crash. So now this system should be listening on that port, offering a command shell. And I can find out by having a second terminal going into my Linux machine. So I can leave this one running. So SSH in. All right, so now that I'm in, I'll do a sudo ss-pant. And I see there is something listening on port 31337. So my exploit has worked, and I can connect to it with netcat. And you see, I've now accessed it. I can now do commands like ID to see who I am. Okay, it looks like it crashed, but I did have it running for a few seconds. I think it is still running. Yep, just I can't see my output for some reason. Something's a little fouled up here, but I am in Dash. If I exit from there, yeah, Control C. All right, Control C gets me out. All right, it may work better if I run it from the outside the debugger. But anyway, it now launched that other program. All right, and I think that'll do for now. Give that stuff a shot. Let me stop this recording.